Okay, so we are now happy that we have looked at what is going on with our good model. With as part of our analysis, we actually looked at boundedness, we looked at positivity of solutions, and I know that some of you are saying, when are you going to talk about the steady states? I will get to that point. Remember, we are following this paper by Howard, so whatever Howard is doing, that's what we are doing. So at this particular point in time, 2.23 is talking about two very important concepts in disease modeling. Actually, these are used for controlling the disease, or at least determining how the disease is going to end at the end of the day. Is it going to continue? Is it going to die out? Or what must be done? I mean, if you are trying to determine control mechanisms, then we must be here at this particular point in time. So, what do we have? We have got two concepts that are here: effective reproductive number, RE, and then basic reproductive number. So we've got two numbers that are given to us and are not, which some of you might have heard about. So when we talk about the effective reproductive number, and in the context of our disease transmission model, we are specifically referring to the average number of secondary infections. So let me just write that down. Average secondary number of infections. Okay, that is the first part that we need to just hold on to. Produced by a single infectious individual. So there is one person who is infectious by a single infectious individual. Right? So that is the first part. And we might need to have more information concerning this idea of effective reproduction number. And the additional information is at a specific point in time. At a specific point in time. At a specific point in time. And I emphasize this fact because we want to be able to differentiate between the effective reproductive number and the basic reproductive number. And the basic reproductive number is going to have the first part, average secondary number of infections. So that is also in the effective reproductive number, it's also in the basic reproductive number. And by a single infectious individual. That is also a fact that we are finding in both definitions, and that's okay. And then the difference now becomes an issue of time because we are now looking at the whole susceptible population. So we are simply saying, given a susceptible population, so we are talking about across the duration of the disease, duration of the disease. All right. So, whilst the effective reproductive number is at a specific point in time, but here we are looking across the whole susceptible population and across the duration of the disease. It's very, very important that you take note of that difference. And it becomes much more visible if you look at the initial susceptible population that we have got here. And we've got, so we are now saying this fraction S naught over n. We have got S over n, which means the fraction of the total population which is susceptible. But we are now saying S naught. We are looking at time 0, and we are saying what fraction of the population is susceptible at that particular point in time. I think it's very, very important for you to take note of the differences that are happening, because as the susceptible population changes, we are going to have some changes. So across the whole susceptible population, across the susceptible population at a specific point in time. It's very, very important to take note of that. So here they are saying that if the entire population is initially susceptible, so in other words, S naught is equals to n minus 1, the total population, just remove one person who is infectious. So the person that we removed here is because he's infectious. There is nobody who has recovered. So if we have got S naught is that, then the effective reproductive number, we replace S naught with n minus 1 over n. B over V here, what it represents is a ratio of the transmission rate divided by the recovery rate, isn't it? And then what it then means is that we have got the transmission rate to the recovery rate. It's a ratio of the transmission rate to the recovery rate. And from that, with the product of B over V and S naught over N, we get an insight into the current transmissibility of the disease, because we will be considering the existing level of the immunity in the population. What are we saying? We are simply saying that RT represents the effective reproductive number at a specific point in time, considering the existing state of the population. And we also put into consideration things such as immunity intervention and other dynamics. And R naught, on the other hand, it just assumes that a fully susceptible population exists, and that's how we calculate the transmissibility of the disease. So which one is more important here, R naught or RE? Well, RE is actually important for assessing the current transmissibility of a disease and understanding how it evolves, because we will be having some interventions taking place. So we need to see how effective our interventions are and how to respond. So the idea is that you then get to be able to control the disease in that particular way. So given our basic SIR model, we have got what is called the effective reproductive number and the basic reproductive number. There is a proof that follows where they say we now show that RE is the threshold value or tipping point that determines whether an infectious disease will quickly die out or whether it will invade the population and cause an epidemic. So we want to look in the next section into the results that we get through a proof to show that, look, it is better for us to focus on RE, which will tell us how the disease is going to come to an end. So these are very, very important measures, and you are going to see that in the next video.